Any question from the problems for this tutorial or previous tutorials or lectures? Okay. The first problem is a mass M, which is suspended from a spring of a stiffness 4,000 Newton per meter and is subjected to a harmonic force having an amplitude of 100 Newton and a frequency of 5 Hertz. The amplitude of the forced motion of the mass is observed to be 20 millimeter. Find the value of M. So in this case, we have the stiffness, we have the amplitude of the response, the amplitude of the external force, and also the frequency of the external force. We need to calculate the mass of the system. The first step, when we want to obtain the amplitude of the response, is equal to delta st, which is the static deflection divided by the absolute of 1 minus r squared. And r is the frequency ratio, and it's equal to the ratio of omega to the omega n, which in this problem, omega is the frequency of the excitation is 5 hertz. And also we have the frequency of the system, which omega n, and it's equal to the square root of k divided by m. Here, the purpose is to obtain m. So we can start from this equation by obtaining the static deflection, which is equal to the amplitude of the external force divided by the stiffness. We know that F is equal to K times by X when we deal with the static problem. So this X is the static deflection. We call it delta ST, and it's equal to F divided by K. So we have the stiffness of this system, which is 4,000. And also we have the amplitude of the external force, which is 100 Newton. So the static deflection due to this force is 0.025 meter. This is the static deflection. Now we can substitute here. We have the amplitude x, which is 20 millimeter. We should convert it into meter. We substitute here for x, for delta st, we can obtain r, which is the frequency ratio. So if we solve this equation for r, we can obtain that r is equal to here 2.25. And now we can solve this problem for omega. So r squared is 2, so this is r squared 2.25, and we can find that r is equal to 1.5. So by solving this term for omega n, which is the natural frequency, we can obtain the natural frequency of the system. We have omega, which is 5 hertz. We should convert it into radian per second. For this purpose, we should multiply by 2 pi, and it's equal to 10 pi radian per second. So omega n is equal to omega divided by r, because r is omega divided by omega n. So if you solve this equation for omega, we can conclude that omega n is equal to omega divided by r. Instead of omega, we have 10 pi in radian per second, and r, which is 1.5 here. Now we can calculate the natural frequency of the system, which is 21 radian per second. And we know that the natural frequency is equal to the square root of k divided by m. And we can find the mass is equal to k divided by omega n squared. And finally, we can calculate the mass, which is 9.07 kilogram. Clear?
Clear, sir.
Okay. The next example, the next problem, in fact, we want to derive the equation of motion and find the steady state response for this system. To derive the equation of motion, here we deal with a bar which has mass or no. This is a uniform rigid bar with mass m, yes, so this is a rigid body. And also we have a particle with mass m. Sometimes in the problems we can neglect the weight of this bar, but here we consider the mass for this bar. So when you write the moment equation, for example, if you use the Newton's second law, and if you want to write the moment equation in the right hand side of the Newton's second law, when you have the mass moment of inertia, you should consider two masses. One is the mass moment of inertia due to this bar, and the other one is due to this mass m. So we should consider both of them. And now we can write the moment equation about point O to extract the equation of motion. For this purpose, we need to plot the free body diagram. We can assume that this bar is rotating about point O in a direction of theta, which is in clockwise direction. So when this system rotating in theta direction, the spring K1 will have one force in upward direction. The spring K2 again will have one force in upward direction because the K2 will be pulled. So the reaction on the bar is in upward direction and it will pull the bar. The spring K1 will be under compression. So the reaction of this spring on the bar is in upward direction. And also we have one external force, which is Ft. Here again, you can see we neglect the weight in the free body diagram because, as I told you, the weight of this mass and the bar will create some initial deflection in these two springs, K1 and K2. So we neglect the initial deflection of the springs, and also we neglect the weight of the mass m and bar with mass lowercase m in the free body diagram and in the equation of motion. So we can plot the free body diagram. Finally, these forces will create the angular acceleration theta double dot, and we can write the equation of motion. So using the Newton's second law, we have 1, 2, and 3 forces, which will cause the angular acceleration theta double dot. So the summation of the moment about this point, which is called point O, must be equal to IO theta double dot. And this IO is the mass moment of inertia of this bar and this mass with mass uppercase M about point O. And theta double dot, which is the angular acceleration. So the moment due to the force K1 A theta is equal to this force multiplied by its arm. The arm is this length, which is equal to A. The arm for the second spring is B, this length, and the arm for the force Ft, which is the total length of the bar, which is L. So we have one negative as well here, you can see, because the moment due to the spring K1 and K2 are in counterclockwise direction or in opposite direction of theta. So we have one negative sign. But the moment due to the force Ft is in clockwise direction, in the positive direction of theta. So this is positive. And finally, it must be equal to the IO theta double dot. This term, third, 1/3 ml squared, is the mass moment of inertia of the bar about point O. You know, for a bar, for example, if we assume this is a bar with mass center G, and this is point O, the mass moment of inertia about the mass center G is equal to 1/12 times by ml squared. This is the mass moment of inertia about the mass center for a bar. If you want to find the mass moment of inertia about point O, this is just to review this equation from dynamic, IO is equal to IG plus MD squared, which this D is the distance between point O and G, this length. And in this case, it's equal to L over 2. If you substitute here, you can obtain that IO is equal to 1/3 mL squared. Okay, so this is the mass moment of inertia for the bar about point O, and the mass moment of inertia for the particle with mass uppercase M about point O is equal to mL squared. Okay, so this is from dynamics, so we can substitute. The first part is for the bar and the second part is for the particle with mass M. Now we can substitute the numerical value and obtain the equation of motion in this form. This is the equation of motion. When you substitute the numerical value from the given data, we have the value for K1, K2, A, B, L, and M. When you substitute here, you can extract this form. As you can see, this is an ODE from order 2 with non-homogeneous term, which is a harmonic function, 500 sine omega t, which omega is 105.
So how did we get the omega 105?
Omega is the frequency of excitation. This is the problem. This is the given data. Let me show you. This is the given data. We have omega, which is 1000 RPM. We should convert it into radian per second. It must be multiplied by 2 pi and divided by 60, and it's equal to 105. This is the omega. Okay, so this is the non-homogeneous term, and to obtain the steady state, because according to the problem description, we only need to obtain the steady state response. So to obtain the steady state response, we only need to solve the particular solution. The particular solution, because the non-homogeneous term is a sine function with frequency omega, the particular solution must be considered a combination of sine and cosine with frequency omega, which omega is 105. Again, you can see. Now we need to obtain A and B, which are the constant coefficient in the particular solution, by substituting into the main equation. Here we need to calculate theta double dot. The theta double dot is the second derivative of theta with respect to time, which is calculated here. And then when you substitute, instead of theta double dot, we substitute from here. And for theta, we substitute from here. And then we can solve these two equations for A and B. The coefficient of sine and coefficient of cosine must be equal to the coefficient of sine and cosine in the right-hand side. In the right-hand side, the coefficient of cosine is 0 because we only have, you can see we only have sine function. So we can conclude that B, the coefficient of cosine here, it must be equal to 0. And the coefficient of sine, which is A, can be obtained from the first equation, and it's equal to this value. So this is the particular solution. And also you can use the formula. If you remember, we have one formula, x times by sine omega t minus phi. And then you can use the equation for x and phi, which here phi is 0 because we don't have damping when phi is 0. So you can obtain x, which x is in fact this A. And you can easily find the amplitude of the response. Okay, any question?
No, sir.
Okay, so this is the second one. The third problem, of course, this problem is mostly related to the concept for this week because it's similar to the base excitation, but the solution procedure is the same. So we can discuss here. For the system shown below, X and Y denote respectively the absolute displacement of the mass M and the end Q of the dashpot C1. Part A, we want to derive the equation of motion of the mass M for this mass. Part B, we want to find the steady state displacement of the mass M. In fact, we want to find the particular response for x when the end q is subjected to the harmonic motion yt, which is equal to y cosine vt. Of course, cosine omega t. This is a typo error, I think. So we need to extract the equation of motion. For this case, we have two damper. One is here, C1, the other one is C2, and one is spring with stiffness K2. We can plot the free body diagram for this mass M, but when you plot the free body diagram, the force in the spring in the damper with coefficient C1, it depends on the velocity of point Q or y dot. So we can write the free body diagram, and this term will appear as a non-homogeneous term in the equation of motion. So we will have one force due to this spring. We assume that this mass M is going to the positive direction of x or going to the right. So this damper will have one force in this direction to the left. The spring will have, similar to the damper, a force in the direction to the left. Also, the damper C1 can have one force in the left direction or right direction, no difference. If you change the direction of this force, you should consider one negative in your equation here. So when this mass M is going to the right, the force in the damper C2 is equal to C2 times by x dot, because one edge is fixed. So the force in the spring, in the damper, sorry, is equal to C2 times by x dot. The force in the spring is K2 times by the displacement or elongation of the spring, which is x, because one edge again here is fixed. So it's K2 times by x, C2 times by x dot. But in the damper C1, we will have C1 times by x dot minus y dot, or C1 x y dot minus x dot. If you assume the direction of this force is to the left, like this that I plotted here, the amplitude or the value of this force here is C1 times by x dot minus y dot. Okay, but here in this free body diagram, you can see that I assume that the direction is to the right. So the force is C1 y dot minus x dot. Okay, in fact, I multiply with a negative sign when you change the direction. No different, the result will be the same. So the summation of these forces in a horizontal direction must be equal to the mass times by the acceleration, according to the Newton's second law. So mx double dot is equal to C1 x dot minus, of course, here.
Say that C1 into x dot
It must
minus
be
y
y
dot.
dot, I think. Yeah, this is y dot minus x dot here. It's a
Say
typo error.
what does that x dot and y dot means? The directions.
The direction, it's up to you. I told you, you can assume that, let me again plot. You can, when you assume that this mass M is going to the right, okay, so this mass will push the spring, the damper, sorry, the damper. So the damper will push the mass, I mean the force will be in this direction. First assume that this edge is fixed, okay? So when mass M is going to the right, the force due to this damper will be to the left, because this is the reaction of the motion of mass M. This mass M will push the C1 damper, and the damper will push the mass. So the force direction is in this direction. Is it clear till now?
Yes, yes, yes.
But now this edge of the damper is moving to the right. So first we have, if this edge was fixed, the force was C1 times by x dot in this direction to the left. Now this edge is going to the right. It means that if x dot was equal to y dot, it means that this damper, the force in this damper was equal to 0, because the velocity of both edge are equal. So it means that this damper is moving as a rigid body. So it doesn't create any force in this direction. So by increasing the velocity of point Q in direction of Y, this force will decrease. So the direction will be x dot minus y dot. The new force is x dot minus y dot. But if you change the direction like this that I plotted for the free body diagram for mass M, when you change the direction, it means that you should change, you should multiply this force with one negative sign. So it will be multiplied by one negative sign. And what does it mean? It means that this time yt, because this yt is in fact more than that x dot. So the direction is in this direction. It means that this point Q this time is pulling the damper. And in fact, this point is pulling mass M. This time we assume that mass M in fact is pulled by the damper, by the force in the damper, and this force is equal to C1 multiplied by y dot minus x dot. This time if we assume that this H is fixed, the force in the damper will be in the right direction because of the motion of yt, and the force is equal to C1 times by y dot. Okay, now we are
Okay.
assuming that this edge is fixed, so the force in the damper when we are pulling at point Q is equal to C1 y dot. This time we can assume that mass M start to move with the velocity x dot. By increasing the velocity of x in the right direction, this force will be decreased by C1 x dot. So it will be C1 times by y dot minus x dot. Both of them will be accepted. I mean, in your equation, if you assume that C1 y dot minus x dot, when you are substituting into the equation, when you write the summation of the force in x direction, this force will be considered positive. I mean, here we will have C1, this is of course y dot, C1 y dot minus x dot because the direction is positive, minus C2 x dot because the direction of this force is negative. The direction of the force of the spring is negative again, and it must be equal to mx double dot. But if you assume the opposite direction, I mean, assume that the force in the C1 damper is in this direction, it will be C1 this time times by x dot minus y dot, okay? And when you substitute into this equation, you need to substitute minus C1 times by x dot minus y dot, because we have one negative, because the direction is negative, similar to the force in C2 and K2, okay? So this negative will affect on this parenthesis, and again, you can extract the same equation. So no different. If you change the direction, we will have one negative here in the equation of motion for Newton's second law. Is it clear now?
Yes, sir.
So we write the Newton's second law and extract the equation of motion, which is mx double dot plus c1 c2 x dot plus k2 x, and it's equal to c1 y dot. This term is the non-homogeneous term, and now we need to solve an ODE with non-homogeneous term, which is harmonic. The yt is y cosine omega t, so y dot is equal to the derivative of yt with respect to times. Y is a constant value. The derivative of cosine omega t is equal to minus omega sine omega t. So this is y dot. And now we can substitute into the equation, as you can see here, and extract the general form of the equation of motion. Now we have an ODE with coefficient of x double dot is m. The coefficient of x dot is c1 plus c2, and the coefficient of x, which is k2. Only we have one non-homogeneous term. If we assumed that this point was at point Q, it was fixed, the equation of motion exactly was the same, but the non-homogeneous term was 0. But here, because this point Q is moving with this function yt, we have one external force, which is a function of the velocity of this point, because here we have a damper. If instead of this damper, we had one spring, for example, something like this, then here in the right hand side of the equation, this non-homogeneous term was k times by y instead of y dot, okay? But the solution procedure is the same. I mean, we have again one non-homogeneous term, one harmonic non-homogeneous term, and we can consider the response in this form. As you can see, the response is uppercase x times by sine omega, which omega is the frequency of the excitation, is the same here, minus phi, and phi is the angle phase. Here we have damping, so angle phase is not zero, and we can calculate the angle phase and x. So this is the response of this system, and also you can find the response directly. I mean, here we have the non-homogeneous term, which is sine omega t, so you can assume that the particular response is a times by sine omega t plus b times by cosine omega t. And then you can find, if we call it, for example, xp, you can find xp dot and xp double dot and substitute here instead of x dot and x double dot, and also substitute here and solve the equation to obtain a and b, then it's constant coefficients into the particular solution and find the particular solution. Or you can use this equation to find the particular response. Okay, is it clear? Any question?
No question, sir.
Okay, and the last problem, for a vibrating system, we have these values for m, k, and c. So we have the equation of motion, which is mx double dot plus cx dot plus kx. A harmonic force of amplitude 180 Newton and frequency 3.5 Hertz acts on the mass. So in fact, by this data, we can write the equation of motion, which is mx double dot, this is m, plus cx dot, this is c, 45, plus kx, which is 2,500 or 2.5 kilonewton. We should convert it into Newton per meter. And it's equal to f naught cosine omega t. So the harmonic excitation, f naught is 180, and frequency is 3.5 hertz. We should convert it into radian per second by multiplying by 2 pi. 3.5 multiplied by 2 pi, which is 7 pi times by t. So this is the equation of motion. And if the initial displacement and velocity of the mass are 15 millimeter and 5 millimeter per second, so these are the initial condition, find the complete solution representing the motion of the mass. So in this case, we want to solve this equation and obtain the particular solution as well as the homogeneous solution. And also we have this initial condition to obtain the coefficient for the homogeneous solution. You can solve directly again. I mean, you can form the characteristic equation, which is 10 alpha squared plus 45 alpha plus 2,500, and then solve this algebraic equation, obtain the roots of the characteristic equation. Then the homogeneous solution is equal to C1 exponential alpha 1t plus C2 exponential alpha 2t. This is the homogeneous solution. And also for the particular solution, you can assume that the particular solution here, because we have cosine 7 pt, the omega is 7 times by pi. So the particular solution can be considered a cosine omega t plus b sine omega t, and then substitute into this equation and obtain a and b. And finally, the x, which is the summation of homogeneous and particular solution. And finally, by using the initial condition, you can obtain C1 and C2, the coefficient of homogeneous response. But here you can see I use the formula. Omega is 7 pi. Xt is equal to x naught exponential minus psi omega nt cosine omega dt plus phi naught. This is the homogeneous response, this part. And this is the particular response. x times by cosine omega t minus phi, which this x naught and phi naught will obtain from the initial condition, and x and phi, which are the amplitude and the angle phase of the particular response, will be obtained from these two equations, the particular response amplitude and particular response angle phase. So we can solve using this formula. And as I told you, because this semester most of your exams are online and you have access to the formula, so you can directly use this formula. But in the exam, if it was not online and if you didn't have to access to your formula and to your lecture notes, you can use the direct method. I mean, you can directly solve this equation using the theory of ODEs to obtain the particular and homogeneous response. Okay, so it's up to you and up to your exam. Any question? Is it clear, this problem?
So this problem is clear. So will our exam be face to face or online? The final one.
uh, till now all of the exams are online. I mean, for example, next week we have short test, it will be online, it will be conducted, but maybe your final exam will be face to face. I'm not sure. We should wait for the restrictions due to the COVID and the conditions in the country. I'm not sure, but maybe the final exam, similar to the last year, we had face-to-face final exam, but all of the other assessments were online. So for now, the shortest one, shortest two will be online, but maybe the final exam will be face-to-face. If it was face-to-face and if you need any formula, I will give the formula definitely to you. No, don't worry about the formula, and you don't need to memorize any formula.
And say about the we having one exam next week, the test one.
Yes, it will be on
Say
Thursday.
on Thursdays.
Yeah.
So what will be the coverage for that one?
The coverage will be till this part, the
This
harmonic
part.
excitation, exactly the concepts which covered till week 5.
Okay.
And I will
So the
explain what's the procedure. We will have 3 different type of questions: multiple choice questions, true, false, and one essay question. I will explain later in the Viber group. I will tell you what is the rules. We will have about 1.5 hours to complete this test, and I think we will have 4 or 5 multiple choice question, 1 essay question, and I think 4 true or false questions, and
okay,
it will
sir.
be conducted online.
Okay, sir.
Okay, no questions? No
No
other
question,
question?
sir.
Okay, thank you, and
Thank you, sir.
have a good weekend ahead. Thank you. Bye.
Same to you, sir.